Hello all, welcome to the class of Discrete Mathematical Structures 18 CS36. Today I'll be teaching a topic in Module 5 Introduction to Graph Theory. The topic name is about subgraphs and complement of a graph. Myself, Dr. Madhura, working as an assistant professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, let us know the definition for subgraphs. Given two graphs, G and G1, we say that G1 is a subgraph of G if the following conditions are satisfied. Firstly, all the vertices and edges of G1 are in G. Second condition, each edge of G1 has the same end vertices in G as in G1. So we say that two graphs, when we consider G and G1, we say that G1 is a subgraph of G if it satisfies the conditions that all the vertices and edges that we are taking in the graph G1 are from the graph G. And each edge of G1 should have the same end vertices which are existing in the graph G. If these two conditions satisfy, then we say that G1 is a subgraph of G. Spanning subgraph. A subgraph G1 of a graph G is a spanning subgraph whenever the vertex set of G1 contains all the vertices of G. The vertex set of G1 and G must be same, and the subgraph G1 in such a case is said to be the spanning subgraph of G. Thus, a graph and all its spanning subgraphs have the same vertex set. Say for example, so I consider this graph G which is in the figure A, then the figure B is said to be the spanning subgraph. So we observe that the figure B have all the vertices which are taken from the graph A. That is the graph G, whatever we consider, that is 4 vertices we have considered, all these vertices are existing in the figure B also, which is nothing but the graph G1 for us. So G1 is a subset, G1 is a spanning subgraph of G. So we observe in the figure C that one of the vertex is not considered. So this is not a spanning subgraph. So the same has been mentioned here. So for the graph shown in figure A, the graph in figure B is a spanning subgraph, whereas the graph in figure C is not a spanning subgraph. It is just a subgraph of the given graph G. Next, we understand the definition for induced subgraph. Given a graph G equal to V comma E, that is vertex set V and the edge set E, if there is a subgraph G1 equal to V1 comma E1, such that every edge A comma B of G is an edge of G1 also, where A and B belongs to the vertex set V1. All the edges that we are considering should be existing in the graph G that we consider in the graph G1. So every edge AB of the graph G is an edge of G1 also. So for whatever the vertex set V1 we consider, for that particular vertex set, we will be considering all the edges that are existing in the given graph G. In such a case, G1 is called induced subgraph of G, induced by the vertex set V1, which is usually denoted by within the brackets like this, we denote V1. Say for example, we consider this graph figure A, which is the graph G for us. Then figure B we have considered, where we consider only the four vertices V2, V4, V3 and V1. So we are considering V1, V2, V3, V4 only, V1, V2, V3, V4 only, and we draw all those edges that are existing in these four vertices being joined. We consider the graph C also. We observe here also we have taken V1, V2, V3, V4. But since V3 and V4 is not joined, this is not a induced subgraph. In the original graph, that is figure A, V3 to V4 there is an edge. So here also V3 to V4 there should have been an edge. So all the vertices that we consider in the vertex set V1, the edges should be marked which are existing in the figure A, that is graph G. So figure A is the graph G shown for us. The graph shown in figure B is an induced subgraph induced by the vertex set V1 equal to V1, V2, V3, V4, whereas the graph shown in the figure C is not an induced subgraph since there is no edge between V3 and V4. As I mentioned, that is the reason the figure C is not an induced subgraph. Next, we consider the definitions for edge disjoint and vertex disjoint subgraphs. Let G be a graph and G1 and G2 be two subgraphs of G. We consider the given graph as G and we are considering the two subgraphs of G as G1 and G2. Then G1 and G2 are said to be edge disjoint if they do not have any common edge. If there is no common edge between G1 and G2, then such a graph is edge disjoint subgraph. Similarly, G1 and G2 are said to be vertex disjoint if they do not have any common edge and any common vertex. So there is no common vertex between G1 and G2 means obviously there will be no common edge at all. So G1 and G2 are said to be vertex disjoint if they do not have any common edge and any common vertex. Say for example, so I have taken up this example where it has 6 vertices A, B, C and D, E, F. Say this is the graph G for us. We consider G1 and G2 as the two subgraphs. G1 and G2 as the two subgraphs. G1 consists of the vertices A, B, C and the edges joined between them. And G2 consists of the vertices E, D, F and the edges joined between them. So this graph G1 and G2 are said to be vertex disjoint as well as the edge disjoint subgraphs. So for the graph G, the graph G1 and G2 are vertex disjoint as well as the edge disjoint subgraphs. See for another example, I consider this graph G for which G1 and G2 are the subgraphs. G1 and G2 are the subgraphs. Now, we observe that there is a vertex common in these two graphs. A is the vertex which is common. D is also another vertex which is considered common in these two graphs. So this is not vertex disjoint subgraphs, but they are edge disjoint subgraphs. Right? Between A to D there is an edge, whereas there is no edge between A to D. A to C there is an edge, there is no vertex C considered at all here. So graphs G1 and G2 are edge disjoint subgraphs, but they are not vertex disjoint. Graphs G1 and G2 are edge disjoint, but they are not vertex disjoint since A and D are the common vertices in G1 and G2. So that's about edge disjoint and vertex disjoint subgraphs. Next, we consider operations on graphs. Consider two graphs G1 equal to V1 comma E1 and G2 equal to V2 comma E2. Then the graph whose vertex set is V1 union V2 and the edge set is E1 union E2 is called the union of G1 and G2. So if I want to write down the union of the two graphs, then the vertex set will be the union of both the graphs and the edge set will be the union of both the graphs. Then we will be able to obtain the union of the two graphs G1 and G2. And it is denoted by G1 union G2. Thus, G1 union G2 is equal to V1 union V2 comma E1 union E2. The vertex set is also taken union and the edge set is also considered to be union. If V1 intersection V2 is not equal to a null set, then the graph whose vertex set is V1 intersection V2 and the edge set is E1 intersection E2 is called the intersection of G1 and G2 and it is usually denoted by G1 intersection G2. So G1 intersection G2 is having G, if at all we want to take the intersection, if at all we want to consider the intersection of two graphs G1 and G2, then it is the intersection of the vertex set as well as the intersection of the edge set, with the condition that when we do intersection of the vertex set, it should not be equal to a null set. Thus, G1 intersection G2 is equal to V1 intersection V2 comma E1 intersection E2 with the condition that V1 intersection V2 is not equal to a null set. The graph whose vertex set is V1 union V2 and the edge set is E1, we have a symbol delta here, E2, where E1 delta E2 is the symmetric difference. So when we are reading this, instead of reading it as delta, we read this as E1 symmetric difference E2, right? That's a symmetric difference of E1 comma E2. This symmetric difference E1 delta E2 denotes set of all those elements. Here it is denoted as the edges which are in E1 or E2 but not in both. This graph is called the ring sum of G1 comma G2 and it is usually denoted by G1 ring sum G2. We'll try to read it once again and understand the definition here. The graph whose vertex set is V1 union V2. So we have the union of the vertex set V1 and V2. The edge set is nothing but E1 symmetric difference E2, where E1 symmetric difference E2 is nothing but the symmetric difference of E1 and E2. The meaning of symmetric difference is nothing but it denotes a set of all those elements or the edges which are in E1 or E2 but not in both. So symmetric difference gives us the set of all those edges which are either in E1 or in E2 but not existing in both of them. So such a graph obtained by doing these conditions or considering these conditions will give us the ring sum of G1 and G2 and it is usually denoted by this symbol G1 delta G2. So this we are going to read it as G1 ring sum G2. Thus, G1 ring sum G2 is nothing but V1 ring sum V2, E1 ring sum E2. For the graphs shown in figures below, their union, intersection and the ring sum is shown. So these are the graphs given for us G1 and G2 and we have the union of these two graphs. The vertex edge is combined, and the edge set is also combined and takes the union G1 union G2. The intersection of these two graphs will be the common vertices and the edges in this. Vertex set is also taken intersection and edge set is also taken intersection. The common vertex set and the edge set is written here. So this is G1 intersection G2 for us. Then we have G1 ring sum G2. G1 ring sum G2. Next, we will move on to decomposition. A graph G is decomposed or partitioned into two subgraphs G1, G2 if G1 union G2 is equal to G, G1 intersection G2 is equal to a null graph. So any graph G is said to be decomposed or partitioned into two graphs G1 and G2 if their union gives us the graph G and the intersection should give us the null graph. Deletion. If V is a vertex in a graph G, then G minus V denotes the graph obtaining by deleting the vertex V and all the edges that are incident on the vertex V from G. So G minus V represents the deletion here. We are deleting a vertex. When we delete a vertex, it in turn says that we are deleting all those edges which are incident on that vertex V. So that gives us the deletion of the graph, deletion of the vertex from the graph. So this graph G minus V is referred as vertex deleted subgraph of G. So when we perform G minus V, that is deleting a vertex from the graph G, this is referred as vertex deleted subgraph of G. Deletion of a vertex always results in the deletion of all the edges incident on that vertex. So G minus V is a subgraph of G induced by V1 equal to V minus the vertex at V. So when we perform G minus V, that is deletion of a vertex V from the graph G, we obtain a subgraph of G which is induced by the vertex at V1, where V1 consists of the vertex at V minus the particular vertex V, one particular vertex V. If E is an edge in a graph, then G minus E denotes the subgraph of G obtained by deleting E but not its end vertices from G. So suppose we want to delete a particular edge, that is from the graph G, we are trying to delete a particular edge, say E, then G minus E denotes the subgraph of G which is obtained by just deleting the edge E. But we are not going to delete it end vertices. We are not deleting the end vertices from the G, only that edge will be deleted from the graph G. This subgraph is called edge deleted subgraph of G. So vertex when we delete, automatically all the edges incident on that vertex gets deleted. Whereas when we delete an edge from the graph G, only the edge that we want to delete will be deleted. The end vertices of that edge G will remain as it is. So this is edge deleted subgraph for us. The deletion of an edge does not alter the number of vertices. The deletion of an edge will not alter the total number of vertices that are there in the given graph G. As such, an edge deleted subgraph of a G is a spanning subgraph of the G. So that is the reason, since number of vertices does not alter from the original graph, it remains the same as it is in the subgraph of the edge deleted subgraph. That is the reason the edge deleted subgraph can be referred as spanning subgraph of the graph G. For the graph G shown in figure A, The subgraphs G minus V and G minus E are shown in figure B and C respectively. The figures are here. So figure A represents the graph G. Figure B represents the graph G minus V. The vertex is deleted. And figure C represents the graph G minus E. The edge is deleted in this graph. Next, we have complement of a simple graph. Complement of a simple graph G is the graph obtained by deleting those edges which are in G and adding the edges which are not in G. So we obtain the complement of a simple graph. We obtain it by deleting all those edges which are there in G and adding the edges which are not in G, and it is usually denoted by G bar. We usually read this as G complement. Note, G and G complement have the same vertex set. Two vertices are adjacent in G if and only if they are not adjacent in G complement. So two vertices, if they have an edge in the graph G, then that edge will be deleted in the complement of the graph. So that is the reason two vertices are adjacent in G if they are not adjacent in the complement of that graph. Complement of a complete graph Kn is a null graph. Kn is nothing but the complete graph where there is an edge between every pair of vertices in the graph. So if at all we obtain the complement of a complete graph, it results to null graph. Means all the edges are removed. So when we remove all the edges from the complete graph Kn, we arrive at a null graph. Fourth one, G complement is equal to Kn minus G. That is, when we are talking about a complete graph Kn and we remove from the Kn all the edges that are there in G, then we obtain the G complement. For example, suppose I consider this graph with the end vertices A, B, C, D and we form a square from this. This is a graph G for us. Suppose we wish to draw the complete graph K4, these four vertices A, B, C, D. If we wish to draw K4, K4 is this, joining all the vertices by an edge. Means there should be an edge between every pair of vertices in the graph K4. Then the complement of G is obtained as G complement. So we observe it is Kn minus G. So K4 minus G gives us G complement. K4 has all the edges being joined, that is AC is also joined and BD also there is an edge. We observe in the graph G, AC there is no edge and BD also is not joined by an edge. So the edges which are missing in G but they are there in K4 should be drawn in the complement of the graph. So G complement is joining A to C and B to D. Self-complementary graphs. A simple graph G which is isomorphic to its complement is called a self-complementary graph. So how can we say that it is self-complementary? We consider a simple graph G and that is isomorphic to its complement. Then such a graph is called a self-complementary graph. Say for example, we consider this graph with the end vertices A, B, C, D. AB is joined by an edge, BC is joined by an edge and AD is also joined by an edge. This is the consideration graph G for us. This graph what we observe is nothing but the G complement. G complement is nothing but the edges which are there in G should not be there in the G complement. You will draw all those edges which are missing in the graph G. That is, A to C there is no edge in G, so we draw an edge in G complement. B to D there is no edge in the graph G, so we draw a edge from B to D. D to C or C to D there is no edge in the graph G, so we draw a edge in the complement. So this is G complement for us. The same graph G complement can be written in this way also. I have just exchanged the vertices B and A, edges remain the same. The position of the vertices A and B are being just exchanged here if we observe, but the edges remain the same. BD, AC, CD. BD, AC and CD are the edges. So this is also G complement for us. Similarly, we observe another graph here, which is written the other way. D and C are taken. Again, the position of the vertices are exchanged. So D and C are at the top here and B and A are at the bottom here. So the graph is tilted down. So these two are also the complement of the graphs for us. So we observe that we started with this graph G and the similar shape of the graph we have obtained in the graph G complement. So since G is isomorphic to G complement here, G and G complement are said to be self-complementary graphs. So a simple graph which is isomorphic to its complement is called a self-complementary graph. The representation of the graph remains the same in both G and G complement. So such graphs are called self-complementary graphs. So with all these basics about the graph, subgraph, spanning subgraph, induced subgraph and complement of a graph, we will move ahead to the problems part. First question, let G be a simple graph of order n. If the number of edges in G is 56 and in G complement the number of edges is 80, then what is the value of n? Suppose G is a simple graph of order n and the number of edges in G is 56. Total number of edges in the graph G is given as 56 and in G complement the number of edges is given as 80. Then what is the value of n? We have G complement is equal to Kn minus G, where Kn is nothing but the complete graph with n vertices. So complement of a graph is obtained by subtracting or obtaining the difference Kn minus G. So from the complete graph Kn, we subtract all those edges which are there in G. So number of edges in G complement is equal to number of edges in Kn minus number of edges in G. So if I want to obtain the number of edges of these graphs, it can be written in the form number of edges in G complement is given by number of edges in Kn minus number of edges in G. So this gives us number of edges in G complement is 80 from the given data. Number of edges in Kn. We recall a property that we had worked out in the basics of graph theory, right? So number of edges in the complete graph Kn is equal to, that is m is equal to half of n into n minus 1 minus number of edges in G. So number of edges in G is given from the data which is 56. So let us simplify this and obtain the value of n. So we have 56 plus 80 into cross multiplying this 2 to the other side. So into 2 is equal to n into n is n square minus n. So this gives us the quadratic equation n square minus n minus 272 is equal to 0. Solving for n, we obtain n is equal to 17 and n is equal to minus 16. Minus 16 cannot happen because number of vertices we are talking about. So n has to be a positive integer. So we take n as the number of vertices in the given graph which cannot be negative. So n must be a positive integer. Thus, order of the given graph G is n, which is nothing but 17. So there are totally 17 vertices in the graph with the condition it satisfies that number of edges in graph G is 56 and its complement is 80. So in such a graph, number of vertices is 17. Second problem. Find an example of a self-complementary graph on 4 vertices and 1 on 5 vertices. We need to draw an example with a self-complementary graph having 4 vertices and having 5 vertices. So we know that a simple graph G which is isomorphic to its complement is called a self-complementary graph. We recall the property for a self-complementary graph. So it is a simple graph which is isomorphic to its complement. So we'll now draw an example on 4 vertices. We consider the 4 vertices as A, B, C, D. This is the graph G for us. And we draw its complement, G complement. So this gives us the complement of the graph G, that is G complement. The edges which are missing in G should be drawn here in G complement. That is how we draw the complement of a simple graph. Now, we observe that it is isomorphic to each other, hence it is self-complementary graph because it looks the same way if you exchange or write the positions of the vertices in other manner, we obtain the same graph as G. Similarly, an example on 5 vertices is taken here. So this gives us an example on 5 vertices. So I have taken a pentagon form. A, B, C, D, E are the vertices and they are joined by an edge. This is the graph G for us and we have G complement. I have kept the positions of A, B, C, D, E as it is. The edges which are missing in G should be drawn in G complement. So this is again a self-complementary graph for us. While drawing a graph with an example of 4 vertices or 5 vertices, we can just keep in mind that 50% of the vertex edges are drawn in the graph G. From the graph Kn, suppose I want to draw Kn for a complete graph with 4 vertices, then it has 6 edges. Then totally it has 6 edges. So 50% of those edges means 3. So try to draw 3 edges in the graph G so that when you draw G complement, even that will have 3 edges. In the same manner, we write an example for 5 vertices for a self-complementary graph. Then we can consider K5. Just recall K5. K5 is nothing but having 5 vertices and there are 10 edges in it. So we can draw only 5 edges in the graph G so that its complement graph also will have 5 edges. If we change the position of these vertices A, B, C, D, E in this, we will be able to obtain a graph which is isomorphic to G. So that is why G and G complement are self-complementary here. So hope these problems have helped you to understand the topic about subgraphs, complement of a graph, induced subgraphs, and spanning subgraphs. Thank you.